So this is section 11.7, part 3. We just finished doing example 3a, where I gave you the initial speed for this cannonball, and we tried to figure out the angle. We're now going to look at part B, where I give you the initial angle, 25 degrees, and ask about the initial speed. So again, I'm going to start just by sketching this. We're firing from ground level, so there's my initial position, 0, 0. We still want this cannonball to go up in the air, come back down, and land at that target, which is 800 meters away. And the initial angle this time, I know, is 25 degrees. What I don't know is the initial speed. So let's see here. Let's say that's just a constant speed k. I don't like s as a variable. I always end up thinking it's a 5. So I'm going to call it k for the speed, or the magnitude of that velocity vector. And that means that my initial velocity is k cosine 25 degrees, k sine 25 degrees, which is our u naught and v naught when we substitute in. So our equation of motion, our position equation r of t, is u naught times t, so k cos 25 degrees, times t. And once again, all of my values here were metric, so the g, sneaking in up here, was 9.8 meters per second squared. So multiplying that by -0.5 would give me -4.9 t squared plus v naught, k sine 25 degrees, times t, plus the y naught, which is 0. So there's my position equation. Again, my goal is to figure out what k is, what the speed is, so that this object lands at 800, 0. So I'm going to say that when x equals 800, y equals 0. So once again, let's set up a system of two equations. Set the x component equal to 800, and set the y component equal to 0. And once again, I'm just going to employ a substitution method. T would be 800 divided by k cos 25 degrees. And I'll just plug that into my second equation. And let's see here. Again, I'm going to do a bit of the arithmetic. On this first term, I'd have -4.9 times 800 squared divided by cosine 25, also squared. Oh, big number here. -3817900.721, and then there's going to be a k squared in the denominator, plus the k's here actually cancel each other out, right? So I really just have 800 tangent 25 degrees, 373.046. And let's just multiply through by k squared to clear the fractions. And k is the only unknown here, and it's pretty easy to get at, so this one's not going to be too bad. K squared would be positive 3817900.721 divided by 373.046. There's k squared. And if I take the square root, about 101.2. And that would be in meters per second, since it's an initial speed. All right, so again, if you know where your object needs to land, you always have to be able to be given, rather, either the initial angle or the initial speed. Given either one of those things, you can calculate the other. Let's look at one more example of this type before we turn to a three-dimensional problem. In example 4, a golfer is playing a hole in which the horizontal distance from the tee to the pin is 200 yards, but the green is on a hill that has an elevation 25 feet higher than the tee. If the golfer hits his tee shot at a 30-degree angle to the horizontal, what initial, and I probably should have said speed, not velocity, sorry, that was a little sloppy. What initial speed will result in a hole-in-one? All right, so let's see here. Since the golfer's teeing off, we'll assume he starts at ground level. The little height of the tee probably doesn't make enough difference to worry about it. So I'm going to call that 0, 0 for my x naught, y naught. And the ball's going to go up in the air, but it's actually not going to come down to the same ground level that it started at. It ends on that hill, which is 25 feet higher than the tee. So it's going to end kind of like this, with a y value of 25. And if it actually is going to make a hole-in-one, the distance to the pin was 200 yards. Got to be a little careful, though. 200 yards, I'll have to think of that as 600 feet to get consistent units. So that's a pretty long hole-in-one, I guess. But that's okay. It's just a math problem, right? All right, so we end here at this point. 600, 25. As far as the initial velocity, we don't know the initial speed. So again, I'm going to call that initial speed k. But I do know that the tee shot was made at a 30-degree angle to the horizontal. So, sorry, it doesn't look much like a 30-degree angle, but we'll label it nonetheless. And so my velocity vector is k cosine 30 degrees, k sine 30 degrees. And last time I didn't have a very nice angle. The 25 degrees would have had a kind of ugly sine and cosine, but 30 degrees is just a nice unit circle value. So maybe I'll go ahead and do the sine and cosine right now. Cosine of 30 degrees is the square root of 3 over 2. And the sine of 30 degrees is 1/2. So I'll use those for my u naught and v naught. All right, we're back in American system with feet. So g is going to be 32 feet per second squared. And r of t is u naught times t. So square root 3 over 2k times t plus x naught, which is 0. And then I've got the minus 1/2 g, so 16t squared, plus v naught times t, plus y naught, which is 0. In order to make this whole in one, when x is equal to 600, y must be equal to 25. So the x is equal to 600 when the y is equal to 25. And once again, this now just becomes an algebra problem. I'll notice here that if I were to solve for t would be 600 times 2, or 1200, divided by square root 3k. So we'll plug that into the second equation. Like so. And a little bit of arithmetic here. I'm just going to go ahead and simplify. Negative 16 times 1200 squared divided by square root of 3 squared would just be 3. Gives me negative 768 with 4 zeros. And I'll have a k squared on the bottom. Plus, let's see, half of 1200 would be 600 over the square root of 3. And here the k's just cancel out. Equals 25. I'm going to subtract this constant. I'm just going to go with the decimal there. So 25 minus 600 over the square root of 3. I can multiply both sides by k squared, which will just bring it over here. And we're just about there. Divide. Gives me 23894.7. And taking the square root, 154.6, let's call that. And that would be in feet per second, since it is a speed. Okay. All right, so that's our process when we know a landing point for solving for either angle, like we did in the cannonball problem, or speed, like we did in both the cannonball problem and this golf problem. One thing I would mention again is oftentimes once you get to the point of plugging the t in, you get kind of a nasty looking equation, and it's often doable by hand, but if at that stage you would rather just graph it on your calculator and solve it using a graphical method, I'm perfectly fine with that as well. All right, I think we're going to go ahead and stop there. Example 5 is actually one that we'll talk about in class, but that's actually going to end up being part of your test, so I'm not actually going to do it with you. Actually, maybe we should talk about it before we put it aside. But this is actually going to end up being part of your take-home test over Unit 2. It says to find the initial velocity vector required for a pitcher to throw a strike. And this is deliberately left quite open-ended. So often in math we just lay out exactly the information you need with no extras, and you just kind of need to learn to plug it into formulas. But the real world isn't that way. So here's one that I'd like you to really do a little bit more as an investigation. Your goal again is to find that initial velocity vector. So your final answer here should be a vector in order for the pitcher to throw a strike. As we saw in the last couple of examples, in order to do a problem like this, you're either going to need to know the initial angle or you're going to need to know the initial speed. My suggestion here is that if you use a few resources, you could probably find a reasonable speed for this pitcher to be throwing. Right? You have your choice. You can do this for a professional ball player. You could do a high school. You could do a little league. I don't care. Just make it clear in your assumptions what you're doing. And go ahead and assume the speed. And then you'll have to calculate the angle before you put it all together as the velocity vector. So, it says start by identifying what information we need to find and what assumptions we'll need to make. I'm going to be asking you then to list them as that. Assumptions, and then known facts that you need. So for example, one of your assumptions is going to be this is a high school ball player, or this is a professional ball player, or whatever you want to assume. Known facts might be things like the distance from the pitcher's mound to home plate, things like that. Okay? So make a list of assumptions and known facts, and then just go ahead and put the information in and solve this problem. Again, I'd like your final result to be an actual velocity vector. So once you've solved for theta, you're going to need to plug it back into that initial velocity vector to give me a final answer. All right? So that's the setup. And again, I'll be asking you to hand this problem in as part of your next test. All right, we will come back and look at projectile motion in 3 dimensions in our next video.